Hello everyone. My name is Ali Behrouz and I'm a PhD student at Cornell and also a research intern at Google Research. And today I'm going to talk about our paper, nested learning, the illusion of deep learning architecture. And although like the main focus of the presentation is about nested learning paper, but generally the concepts that I will explain or the examples that I will discuss are mainly based on four papers that we have done in this direction. And so generally, like if we think about the shortcoming of the current LLMs and like what are the limitations, we know that with the rise of transformers and also scaling them, everything in AI has been changed, and we could come up with a lot of applications for AI systems. And so the main like advantages of transformers was that instead of designing some task specific systems, with transformers we can design general purpose systems because they have more adaptability, and also they are capable of doing in context learning, fusion learning, and all these kind of things. And but the point is, like with the current architectures, we can see that uh, they're still not as good as we expected in, for example, long context efficiency, in capturing knowledge abstraction, and generally, like they are not very robust. They cannot adapt fast to the context. And in a very, very general form, when we have all these kind of things, we can say that they are not capable of continual learning. And I wanted to emphasize on one important component because unfortunately with with more, I mean, continual learning is gaining more popularity, but the point is, uh, everyone has their own like definition of continual learning, and they're come up with like new definition. And so more and more people are trying to like advertise their method to claim that it's related to continual learning. But one important component, in my opinion, is that if we have an actual continual learner, then there is no test time in it, there is no train time in it. And so if we see these terms somehow, like potentially it's not an actual continual learner. And so if we want to like design models that are capable of continual learning, we need to fade the uh, a border between the test time and train time. And so basically that's one of the important component when we are saying something is doing continual learning. And now let's, look at the current LLM paradigm, like what is their main like issue. So, they are very great when we could somehow fit what we want in the context. So LLMs are great when they want to adapt to their current context. But the fact is, their long-term knowledge is very limited because there is a knowledge cutoff when the pre-training of the model has happened. And so after the pre-training, there is no specific update on the knowledge of the model. So you can simply see that if you ask some questions about like the current events, very, very recent events, and then you just like ask the model to not use any search or any other tools, you will see that they would say, I have a knowledge cutoff and I'm not aware of that specific event because it's after my knowledge cutoff. So the question is like, what is the issue? They're great in context. When the context is gone, then the knowledge in that context is also gone. And the interesting part is there is a very interesting similar connection to one specific condition in humans, which is called anterograde amnesia. And generally after the onset of this specific condition, we can see that there is an inability to form new long-term memory. So basically the person can keep their memory before the onset of this condition, so that's unchanged, but they are like experiencing the present over and over and over, and there is no shape of new long-term memories, and also the main reason for that is there is no transfer from the short-term to long-term memory. And that's, I think, very interesting because in this condition, the long-term memory is there, the short-term memory is also like there, and there is no issue about like having those components. But the main issue comes from the knowledge transfer between the short-term and long-term memory. So that's generally like what we are trying to address in this series of work. And so basically a lot of things that we are building on are based on this concept of associative memory. So what is associative memory? Basically, associative memory is a fundamental concept even in human learning, and mainly is referred to as the ability to remember the relationship between relevant or irrelevant event items or anything. And from the technical point of view, we can look at like associative memory and view it as a dictionary. So basically we have keys and values, and we want to like map keys to values based on the data. So generally, if we want to learn from data, you can define the learning process as acquiring the mapping between keys and values. So in the training phase of associative memory, we can say that there there is like input key and then there is an output value. And when we want to do inference, then there is a query and there is value again corresponding to that specific query we have. Now let's just like formally define what I just explained. We have a set of keys and values, and we want to learn an associative memory, so it maps keys to the values. But the point is, if we want to have a learning process, we need an objective that measures the quality of mapping between keys and values so far based on the data. And let's assume that it's like LTILA, and so the mapping here that we want to learn is component M. And so generally we can say that associative memory is the solution to this optimization problem that is trying to minimize the measurement of the quality of mapping. So basically if we have a perfect memory, this objective should be zero. And so we are trying to like learn that mapping from the data. There are like very simple examples of this objective. For example, we can see the process as a form of regression and say that, let's assume that this mapping is just a simple linear function, and then M is a, a matrix. And then, for example, we can simply say it's a regression or generally prediction task, regression task, where we want to predict the value of V based on K. So the output of the model would be M times KT, and the actual label is VT. So if we maximize the similarity of these two, then we can say that we have a perfect memory. Or another case, if we minimize the difference between these two, then we can say that we have a perfect memory. And there are a lot of like design choices here that we can make. So for the case of this simple dot product similarity function, we can say that I just want to like minimize the this objective using gradient descent or any other form of optimization problem. So in the first part, after understanding this associative memory, we want to see that all of the architectures that we know of, everything that we have in the literature are a form of associative memory somehow. At least the novel components that we are using more and more in recent years are a form of associative memory. So let's just start with some simple examples. The first example, is the one that I just mentioned. Let's say we have a dot product similarity between the output of the model and also the value function, which is the ground truth, and then use a simple gradient descent to optimize this objective. So what would happen is that we just need to write the gradient descent formulation and then take the gradient. The gradient of this function is basically VT times KT transpose. And then if we just like replace it in this formulation, we will see that we will come up with the formulation of linear attention. So the formulation of linear attention is based on Hebbian rule, and we can see that like optimizing this objective is equivalent to the Hebbian rule and linear attention that we all know about that. So it's a fully like equivalency between these two concepts here. And so now we can better understand what linear attention is doing. Linear attention is basically an associative memory that is trying to map the keys and values and use this specific objective to measure the quality of its prediction. Now let's go to the another example. Let's say that I want to use the L2 regression loss and again use a simple gradient descent to optimize this regression loss. And if I calculate the gradients, I will come up with this term. If I replace it and simplify everything, then I can see that the final model design is based on this delta rule that is happening here, which is the work of Schmidt-Haber et al. So in 2021. And so, in both these cases, we assume that the architecture of the memories is simple linear function or matrix. And also we can see that with the simple choice of optimization process, which is just a simple gradient descent, we can come up with linear attention or this delta rule. And now, when we were thinking about all these kind of like equivalency, we see that, there is a pattern, there's a simple pattern here. We can design an architecture or generally a causal sequence model based on the concept of associative memory. And there are four different design choices there. One is the memory architecture. So do we want to like learn a mapping which is a vector? I mean, the transition matrix is a vector, or it's a matrix, or it's a neural network, or it's even like more complicated neural architectures, and so on and so forth. So basically, that's arbitrary, and we can use any arbitrary memory architecture that we want to use. And the main point is, the more expressive the memory architecture is, the more capacity we have to compress the context. So if we want to go to super ultra large context, for example, 2 million, 10 millions, or like even larger than that, we need to like use more powerful structure for the memory architecture. And then another one is the attentional bias. Basically, this attentional bias is the name of the objective that we use to measure the mapping between keys and values. And then also we have this like retention gate. What is the retention gate? Retention gate determines how much information do we want to retain from the past state. For example, if we want to say that I don't want to like retain anything from the past, it means that I just want to forget everything from the past and start from the scratch now. Or I want to like retain some part of the information. Some parts are important, some part are not. And the question is like which part is important, which part is not. And so basically the choice of this retention would control that. We can use like LP regularization, we can use elastic net regularization, KL divergence, Bergman divergence, and anything like that. There are a lot of design choices there. And finally, the last design choice here is memory algorithm. So for example, you can say that I have gradient descent momentum. I want to use Newton methods, or even I want to find the non-parametric solution to that objective function. So I just want to like emphasize here on something that you might see that, for example, not all of the architectures has this formulation of keys and values. But the point is, you can just simply assume that keys are like identity matrix, or V's are identity matrix, or just like identity vector. And so basically here we have a very general formulation of the associative memory, and with different design choices you can come up with a lot of architecture designs that are already in the literature. As some examples of it, you can see that softmax attention is a non-parametric solution to the following objective. So if you want to solve this objective, find a linear mapping and solve this objective over the context of 1 to L, then you will see that the non-parametric solution to this objective is like as this one. And with the simple design choices of S equals to exponential function, then this is equivalent to softmax attention. So basically, we can see that softmax attention is very powerful because it's actually a non-parametric solution to this objective. And, we see that, for example, we can come up with Hebbian rule, or recently it's more referred to as linear attention, using like this dot product similarity. Or, for example, we can use L2 regression laws to, for example, come up with this design. And so in Titans, what we have is basically we use this L2 regression loss, and then instead of a simple linear matrix here, we use a deep MLP block. So it can be any neural network optimized with like the optimization process that we have. And then for the choice of optimization problem, we use weight decay plus gradient descent with momentum. So that's a little bit more powerful optimization process rather than the simple case of linear attention or anything like that. And also linear attention, or most of the linear RNNs that we are aware of, are based on simple matrix, but here we have more capacity to go like to longer context and can like you know, learn a very powerful mapping between keys and values as well. And in the literature, we can see that there were a lot of like efforts in this direction to go to more powerful learning rules. For example, there is OER rule that they try to add this specific regularization term to the dot product similarity to make the Hebbian rule more powerful. And then also in the Atlas paper, we have present this omega rule, which basically says that, all the RNNs that we are aware of are just online learner. And what does that mean? It means that they are optimizing their memory once at a time in a stochastic manner based on the current token that is like given. But the point is, it can cache some of the tokens, and at each time, it optimizes the memory based on a past local window of tokens, not just a single token. So that's a more powerful way to optimize the memory. And so we argue that instead of like memorizing the tokens, it's trying to memorize the context. And so generally, that's a very important component for that design. And we see that linear attention, because this omega rule is very general based on an arbitrary objective here that you might want to have. But the point is, if you, for example, choose this objective as here we see that linear attention is equivalent to dot product similarity of this. Now let's say that we replace this objective with dot product similarity, and we will come up with a sliding window linear attention design, where we simply like update the model very similar to linear attention, but instead of looking at only the last token, we look at a local context window of the past tokens. And for example, for the special case of context lengths of 2, you can see that we will come up with this specific memory update, which says that instead of updating the model based on only VTKT, we update it based on VTKT and also VT minus 1, KT minus 1. So that's one way to look at all these problems. Another way is that when you update your memory based on only VTKT, then you are updating the model based on rank 1 update. But if you go to like more tokens and cache them and update the model based on that, then you will come up with more powerful structures where the update is like arbitrary rank that is happening in this recurrent formula. Now, so far we have seen that all the architectures can be, that we know of. You can check the paper for all the details, but yeah, generally all the modern architectures can be written in this optimization process. And now let's go to another component of generally neural networks, which is optimization algorithms, and generally the concept of backpropagation. So let's start with the simple example. Let's say I have just a simple linear matrix that I want to train on a supervised task that tries to map xt to yt. So I have this arbitrary objective function. I want to train W here. And so, let's say that I just want to use simple gradient descent to optimize this linear matrix. And then, if I just write the gradient descent formula, I can rewrite this component, this gradient component, based on chain rule. And that's what we do for backpropagation process. So I would have this gradient with respect to the output, and also uh, this will be multiplied by the input, which is xt plus 1. Now let's say that I just want to call this gradient component as ut plus 1, and we can simply see that this update rule that I have here is equivalent to solving this specific optimization problem. So if I solve this specific optimization problem, then I can see that WT plus 1 would be equivalent to what I have here. And now let's look at this process. You can see that it's very similar to associative memory because, for example, this UT plus 1 is the value and this XC plus 1 is the key. And then I want to find I want to minimize this dot product similarity that I have here plus a regularization term. And so that's actually the definition of associative memory. So it seems that at least backpropagation using gradient descent on a linear matrix is a form of associative memory. And in the paper, we just extend that to any arbitrary neural network, and we can see that each layer, the backpropagation process for each layer is a form of associative memory that is trying to map the inputs of that layer to the error rate causing by that layer to the output. So basically, we can see that generally the backpropagation process is a form of, associative memory. And now, we can go to more powerful optimization process. For example, we can say that we want to use gradient descent with momentum. But the interesting part is if you write the momentum term, you can see that the momentum term is again a form of it's a form of associative memory because it's a recurrent formula, and you can see that this recurrence that we have for momentum term is equivalent to minimizing this dot product similarity objective when we want to find the momentum. So from this perspective, we can say that momentum term is an associative memory for the gradients. So basically, momentum is trying to compress the gradients. And it's very similar to memory. The context of the memory that we know is a token space. But now we are talking in the gradient space. So it seems that all of them are the same, but there are some minor changes. Now, unfortunately, there is a misunderstanding in the literature saying that gradient descent, or generally this backpropagation process for a linear matrix, which here we extend that to any arbitrary neural network, is a form of linear compression or linear attention. But the point is, if we just simply look at this process, you will see that, oh yes, this associative memory is optimized based on dot product similarity, and also it can be written as this one, which is equivalent to linear attention. If I write gradient descent with backpropagation process, then again, it's very similar. But the point is, there is a very interesting difference between these two, which make gradient descent not a form of linear recurrence or generally linear attention. And the point is, this value that we have here, this term of the value we have, in the linear attention, keys and values are given. There is no optimization process on that. But in the gradient descent formulation, this value is generated by the model itself. Why? Because, we just need to recall what was the value. The value was this gradient, and this gradient is a function of WT as well, which is the state of the memory, which is the state of the current memory. So it seems that there is an important difference between them. In the linear attention, keys and values are given, but in gradient descent, the model generates its own value. On the other hand, in linear attention, the only thing that it needs to do is to learn the mapping between the given keys and values. But now the model here needs to learn how to write its own update rule, because how to come up with this W function, this value that we have here, is a form of like controlling its own update. And then we can see that this linear attention is parallelizable. We can just simply write and expand the recurrent formula and then write it as a simple matrix multiplication. But the point here is that it's recurrent by nature and we cannot parallelize it in the current form. And finally, based on all these points, we can understand that linear attention only learn a linear mapping between keys and values, but this formulation of gradient descent is very more complicated than the linear mapping, and it's nonlinear, and learn a nonlinear compression process. So I'm not going into the details, but generally in the paper, we go into more discussions about optimizers, how we can write them in as a form of associative memory. Just two interesting examples are Adam and Ada grad. In the paper, we discuss that Adam and Ada grad are optimal solution of these objectives. And what are they? They are trying to map the local information to a global representation of the objective landscape. And so it seems that what they're trying to predict the global landscape based on only local information. And if we solve them to the optimality, we can come up with the Adam and Ada grad optimizers. And so, all these things are just like some findings, but the point is, how we can use all these understandings. So in the paper, we generalize some well-known concepts. For example, instead of a simple gradient descent, because we saw that gradient descent is a form of like dot product similarity, optimization of the dot product similarity. So now we can just simply change that to L2 regression loss to come up with a more powerful update rule. So we present this delta gradient descent, which is simply just gradient descent, but we have a data-dependent weight decay process. Or simply we can just apply the same intuition for for momentum term and come up with a new formulation to update the momentum, and we call this variant delta momentum. So far we see that, architectural optimization problem, optimizers algorithms are again optimization problems. So now let's just combine these two together, and we can see that everything is just a form of nested optimization process. All of them are a form of associative memory. And why it's important? Because if we look at the from the deep learning perspective, we can see that we only see the final solution. But on the other hand, when we look at that from the nested learning perspective, we can see all the internal learning process, and we can go beyond that. So I'm not going into the specific formulation of the nested learning here, but I just wanted to emphasize that when you have multiple levels in the nested learning, which each of them are defined based on the concept of this update frequency, which means that how often do we want to update that specific block. And then you will unify all the important concepts that we are aware of. For example, you can come up with the meta learning, you can come up with attention, RNN, momentum term, and everything like that. And the main points, how we are differentiate between all these concepts, is about how we do knowledge transfer between different levels. For example, we can say that if I have two levels, then I will consider the output of one conditioned on the output of the another one. When I do that in a parametric manner, then I will have recurrent neural networks. If I do that in a non-parametric manner, I will have attention in transformers. Or, for example, we can have knowledge transfer using backpropagation, which is what's happening in layers in deep neural networks. Or we can do knowledge transfer via initialization, which is equivalent to two-level variants of model agnostic meta learning. Or we can come up with other like design choices, for example, hyper networks, optimizers, and architectures. So generally, it's a very, very general formulation. And then, based on all these understanding, I'm going to like talk about the final architecture that we have. So in Titans, I explained that we use L2 regression loss and then optimize it using gradient descent with momentum and weight decay and use deep neural network. But now we want to extend it to self-referential models, which is very similar to gradient descent. We want a model to generate its own value in the process. So that's the first component that is changing here. The second component is we replace gradient descent with our design of delta gradient descent. So that's the second part. So in our sequence model, the first component is self-referential Titan model, which is Titan plus these two changes that I mentioned. The model generates its own value, and also it used delta gradient descent instead of gradient descent. And then we have another component here, which is a self-modifying Titans with continuum memory, which we call this architecture as HOPE. And what is continuum memory system that we are presenting here? It's basically just simple MLP blocks, but each of the MLP blocks are updated with different frequency. So if we have like 3 MLP blocks, the first one is updating very fast. The second one is updating with like, in the middle frequency. And then I have a more persistent long-term MLP block. So all of them are trained end to end and use next token prediction loss to update their weights. And so what we are doing here is that we are meta learning the initial state of each of these MLP blocks so they can adapt fast to the context and update themselves. And why this design is important? Because it provides a loop in the time dimension. So, if I want to update the model, there is a potential that it face catastrophic forgetting. And so potentially this fast updating MLP block can simply forget something. But the fact is, when it forgets something, these two components are not updated so far. So the information is already there. When I do back propagation process, this information can come back to this MLP block. And then it can remember something from the past. So that's generally the process and the design of HOPE architecture. And also in the paper, we have HOPE attention. So the HOPE attention is basically a transformer block. We have this attention block here instead of self-modifying Titan, but instead of MLP blocks, we use this continuum memory system using multiple MLP blocks. All of them are training end-to-end using next token prediction. When your task is language modeling. If your
So
task is
Ali,
about
we
vision,
have a quick time check, 2-minute
sure,
warning.
sure. And so if you want to like go to other tasks, we can simply just change the objective here and come up with the other form of the update route. So in the experiment part, I don't want to like go into the details of like numbers, but the point is generally we have some experiments on the language modeling and common sense reasoning task, and we see that this HOPE architecture that we have show good performance compared to all the linear RNNs and also deep RNNs and also transformers. And so generally it shows very good performance in language modeling. And the most important part is about this long context modeling. We have a task and we increase the context to even 10 million, and we can see that like a lot of models, even ultra large model like ChatGPT 4 and or Llama with 8 billion parameters, all of them are face issue when they want to scale to larger scale context window. But for example, for this HOPE, we achieved like more than 90% even with 10 million of tokens. Thank you very much. And generally, like these are the main references that I use in this paper.